Okay. So everything is clear now? So we can start now.
Yes.
Huh. So just let me check whether everything is clear. Everything is clear. So today is this is tutorial 12, tutorial 12, advanced linear algebra. NOC 25 NA03, and today is um, 12th. Today is 12th April. 12th April. Okay, so before starting the class, I just want to make an announcement, and that is regarding an extra class. I think date is 15th. Yeah, there will be a class. There will be an extra class, extra tutorial on 15th April from uh, 7 p.m. to 9 p.m. And obviously, you will get a mail from the NPTEL team. But I just, uh, I just, I just, um, I just inform you, so that you may keep in track. If you miss the mail or something, so the same link, everything will be same. Huh? Okay, the same link as same Gmail link. This is that will not be from 6 p.m. to 8 p.m. That will be from 7 p.m. to and 9 p.m. And I mean, I may discuss some of the problem of quadratic equation on that class. Maybe today I will not discuss that much of in quadratic equation. So, I got your questions also. I have downloaded some of them. So let's try to do some of them at least, and after that we will. Okay, first I will do half an hour some of the problem of that, and after that I will do the assignment problem, which will be regarding the next assignment 12 problem, and next I will do some whatever the remaining time will be there, and I will do the other questions. But hopefully I will not touch for today the quadratic equations problem, because those I will try to do in the next class, and today mainly I will focus on the normal operator and all those. So let's. This is the last problem. Okay, this one is a problem you sent. I hope it is visible, right?
Yes.
Uh, So what it says that let A be a 100 by 100 matrix with the entries Aij is such that Aij is equals to I if I plus j is 101. Okay, and Aij equals to 0 otherwise. So just try to first before go. I mean, before going to these options, just try to see what is the matrix, because this is very interesting thing. You will not get this. I mean, must be a pattern. There is a pattern, and we are trying to find out what is that pattern. Okay, so that will obviously directly help to solve the problem. For example, if I consider A is an n by n matrix. Okay, this is same thing. So let's consider the simplicity. Let's consider the 3 by 3 matrix: A21, A22, A23, A31, A32, A33. Now, if you note that I plus j and accord in this diagonal is 2, that is equals to 2. I plus j in this diagonal, I plus j is equals to, that is, in this diagonal it is 3, in this diagonal
3,
it is 4,
4,
in this diagonal it is 5, and in this diagonal it is
5,
6,
6.
right? So there must be a pattern. So you know that there is an 101. So whenever it is becoming n plus 1, that is the cross
I.
diagonal. That is the cross. Oh, no, sorry. This is 3 by 3 matrix. So cross diagonal, right? 4, I
Yes.
need to get 4. So this is cross diagonal. So you know that for if I even if I take an n by n matrix that way, like 1 1 to n, a 2 1 all the way to n, this way a n 1 all the way n. So you'll obviously get the cross diagonal for which I plus j equals to n, right? So
Yes.
what it is says is that the entries in cross diagonal is I. Okay, so that means this entry, if I plus j is 100 and 1. So in this situation, I is equals to n. In this situation, I is equals to, okay. So in this diagonal, it is I plus j equals to n, that I understand. But okay, in this entry, this is I equals to n, but this entry I equals to 1. So what will be the matrix? Then matrix A is equals to something like 0 0
1
0
to
1.
100 in anti-diagonal.
Right, 0 0, this is 2 and 0, all the way it will go n 0 0 0, like this way, right?
Yes, sir.
This is the cross diagonal. This is the cross diagonal. This is the cross diagonal. I plus j equals to 101. So this is n plus 1. Okay, so n plus 1. So therefore, you get the matrix. So what is the questions? Next look at the questions. Which of the following statement are true for about n? A is similar to a diagonal matrix over R. A is not similar to a diagonal matrix over C. One of the eigenvalues of A is 10, and none of the real eigenvalues of A exceeds 51. Okay. So what are the options? A is similar to a diagonal matrix over R. So I think this is not true. First option is not true. So why the first option is not true? First option is not true. A is similar to a diagonal matrix over R. So for that, I will take A is equals to 0, 1, 2, 0. For example, this one. So yeah, for example, this one. Then what is that A minus lambda I? That will be that will be lambda 1 A minus lambda I. So minus lambda 2 minus lambda, right? So this will be the determinant will be lambda square minus 2. Oh no, this is happening. This is happening. Sorry, this is the wrong example I took. So sorry. So what was the questions? Let me read it. A is similar to diagonal matrix over R. A is not similar to a diagonal matrix over C. None of the eigenvalues of A is 10. None of the real eigenvalues of A exceeds 51. Cross diagonal is this one. Okay. So if we consider the transpose, that will be zero. I. For example, okay, for easy one, let's take a easy example. Let's take 0 1. Let's take a 3 by 3. I think this is, I mean, you don't need to do obviously all the way. You can check it for 3 by 3 and guess whatever, and after that you can prove. But I just want to do it complete formally. But let's do this one. That was not feasible to me right now. If A is equals to this, then A minus lambda I, that will be minus lambda 0 1 0 2 minus lambda 0 3 0 minus lambda, right? So what is the determinant? Determinant is minus lambda into 2 minus lambda into minus lambda. Okay, and next one is plus 1 into 0 minus 3 into 2 minus lambda. Please look at if I'm making any mistake. So then it will be 2 minus lambda into minus lambda into minus lambda into 2 minus lambda into minus lambda plus 1, that was the third term, that's a plus 1, 0 minus 3 into 2 minus, so therefore it will be lambda into 2 minus lambda plus minus 6 plus 3 lambda. So therefore it will be 2 lambda minus lambda square minus 6 plus 3 lambda. So that can be written as lambda square uh, minus 5 lambda plus 6 equals to this one. So therefore one can write this one is the minus lambda minus 2 lambda lambda into 2 lambda minus 3 equals to 0. So this is the polynomial. So this is the polynomial. So therefore lambda equals to 2 and lambda equals to 3 are the eigenvalue. So what you can get is that there, but I think we should get here the, okay, 3 by, that is the mistake again I'm making. This will be 2 lambda square minus 3 lambda minus 6 plus 3 lambda. That will be 2 lambda square minus lambda cube. So that will be minus lambda cube minus 2 lambda square minus 3 lambda plus 6 is equals to 0. So if you replace lambda equals to minus 1, if you replace lambda equals to minus 1, what you will get? That replace lambda equals to minus 1, it will minus 1, minus 2, plus 3, plus 6. There is no point. If you replace lambda equals to 1, what will get? Lambda equals to 1, 1 minus 2 minus 3. That is also not giving anything. One of the eigenvalues of A is 10. Okay, so A is not similar to diagonal matrix over C. A is similar to diagonal matrix over R. A is not similar to diagonal matrix over C. One of the eigenvalues of A is 10. None of the real eigenvalues of A exceeds 51. Yeah, I understand there is the trace element is the 51th element is the trace element. So 51 is the 1 to n, 1 to 100. This is 100 by 100 matrix. So there is no diagonal. Okay, so we have to consider a little differently, not this one.
Sir, I think trace will be 0.
Yes, trace is 0. That's true. That's true. Trace is 0. That's clear. Trace is 0. So trace is 0. That's true. But if trace is 0, okay. If trace is 0, that you can look at for this one. So that is wrong example actually. We can't take n is. I mean that depends whether n is even or odd. That depends there. Okay, you can't take 3 by 3 because
Sir,
yeah.
this matrix is similar to a matrix, a block matrix, sir, whose
No,
first block is, sir, 0, 1, 100, 0. Second block is 0, 2, 99, 0.
sorry.
Sir, 0, 1,
Huh?
100, 0.
So after that
0,
100 0
1, yeah, 0, 1, 100, 0, sir, row wise.
row wise 0.
Block, this is a, sir, block diagonal matrix where, sir, blocks are 2 cross 2
Okay,
blocks.
two. Okay, what are
So
the blocks? 0 1
blocks
0.
are 0, 1, 100, 0. 100.
Here it will be 100 0 here.
No, 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 sir. Zero, sir. I'm talking about blocks, sir.
Huh?
First row is 0, 1, and second row is 100, 0.
Okay, second row
Block of
is 100 0 like that,
no,
right?
no, no, sir. 100, 100. Entries are 100.
Here is a 100. Here is a 100.
Second entry of, sir, the second first entry of the second row is 100,
And after that,
and then 0, then
oh,
0.
so this year you are saying
Yes.
that this type of matrix, right? Another is a 0.
And yes, sir. Second block is, sir, 0 to
So
99, 0.
this is the block, right? Second
Yes,
block
sir.
you are saying is 0 to
Ah,
99 0. This is the block.
yes, sir.
This
And
it will
so
go.
on.
So
Yes,
on.
sir.
So therefore, if you say that way, then lambda square minus 100.
Ah,
So
ah.
so whatever the eigenvalue, that eigenvalue will be the same with the eigenvalue of this one, right?
Yes, sir. Yes, sir. This is because block diagonal
So
matrix.
last one will be hopefully 0. This is 2
100,
to 50 50, right? 0 2.
0,
Last one will
50.
be 0
Ah,
50 50.
ah.
No, 0 51 0, right? Like that.
Yes, sir.
I think this one is the last entry, right? sum is 101, something like that.
Yes, sir. 51.
51, 0, 51, this way. So if you
Hmm.
say this way, then what will be that lambda square minus, first one will be lambda square minus 100, second one will be lambda square minus
2 into
like 99
99.
into, so that will be one, whatever that, 99
2
to
into
a 190,
99, sir.
29,
Uh,
that way it will
yeah.
go. So therefore
Yeah.
the eigenvalue is equals to like lambda equals to 10, one will be eigenvalue, and another
Uh,
eigenvalue will be like lambda, this way it will go, and the last eigenvalue will be like lambda square minus 51 into 50, this one corresponds, right? So
yeah.
therefore if you show that way, then one is the, first of all, one of eigenvalue is a is 10, that's true, right? And other eigenvalue is plus minus 10, and so therefore here it will have all other eigenvalues there, so therefore a is diagonalizable over r, a is similar to diagonal
Yes.
matrix over r, this one is
Hmm.
also true then. And if a is not similar to
Yes, sir.
that, then obviously this is a is not similar to none of the real eigenvalues of a exceed 51, that will also be true, because this one, because
Yes.
you know that maximum
Uh,
eigenvalue you will get here, because this is the maximum product
uh,
will be. So, but this is lambda square equals to, if I write 51 into 50, so therefore we can write it as 50 plus 1 into 50, like that way. So
yes, sir.
therefore
Will
it
not
will
get
be,
51.
so
Less
that's what
than
I think.
51.
So less than, so lambda will always be less than equals to 51, because that is less than equals to 51 square. That is strictly less than equals to 51 square. So therefore lambda will be strictly less
Yes.
than 51. So none of the eigenvalue will exceed 51. That's true. But why this matrix will be like this form, similar to this form?
Sir, any anti-diagonal matrix,
Yeah, there
sir,
obviously there must be something like that. I understand, but
yes, sir. If we take S as, sir, E1, En, E2, En minus 1, sir, where E1 as, sir, column wise, sir, E1 like column 1000, and the En is 00 at nth place 1.
okay, you are saying that we can interchange, right?
No, no, sir. I am talking about the similarity, sir. How can we put
Why this?
both matrices?
Right, right. We have to
We
show that these two are similar. That means there must exist an unitary matrix U such that A U U
yes, sir.
equals to A inverse or A star, that is A star, or A inverse actually. There will be, that is same thing.
Yes, sir. So I am
Yeah.
talking about
A
that
inverse, that
U,
will be
sir.
this one. So what will be the matrix U then here? U will be, you are
Yes,
saying
sir.
that just
U
in
is, sir.
E2,
Hmm.
E1, E4, E3, like that way.
Now, E1, En, E2, En minus 1, sir.
Oh, that way. Okay. Take E1 equals to, yeah, that's true. That's good.
Hmm.
Let take E1 is equals to, take U is equals to
Uh,
E1 En
En,
E
E2, En
E2
minus 1.
En minus 1. Yeah, that's true. That's true. E50.
No, sir. We are taking N, sir.
E50.
So
You are taking N.
so
So
on, sir.
soon, but there must be end. No, this is 2. I will have 100 only, right? So
100.
this way you will get here
It will depend
A50.
upon N, sir.
Yes.
Sir, it will depend upon N, sir.
Yes, this, but if N is 100, then what I will get?
So first put, sir, N
That
as
will be
100.
E49 then. Then this will be E50. E50.
Hmm.
This is E100. This is
Hmm.
E99.
Yes.
So this is will be like
Some
50
is,
into
sir,
100
100.
minus 51, like that way.
Some is 101.
Some will be 101. Some will be 101. So therefore this is 51 then. 51, right? Yeah, that's true. That's true. You have to get where ei is equals to column vector, that is 0, 0, 0 at I position 1 on all other integer. That's very good trick.
Yes.
1
And
at,
also the, sir, matrix you have written is actually, sir, S inverse AS.
yes,
Sir, the
yes, this
matrix
one. This matrix is
actually,
this one.
this is S inverse actually, sir. S inverse. Matlab UA.
Okay, okay, okay. You are saying that this one will be right.
This is, sir, UA inverse. This
So that is
matrix is.
doesn't matter. That we have to change the matrix. Yeah, thanks. This is
But
actually,
but sir, in that case, if we take U as this, then
then it will be,
we
I think,
will get.
order will be changed, right?
Yes,
Or,
sir.
but yeah, if it is working like that, I mean, we have to get an inverse matrix. Let's take U inverse is that matrix for which you are getting. That doesn't matter.
Yes, sir.
Yeah, that's
So
good. Good
then
thing.
if we consider u inverse u inverse u inverse u, then it will be a simply, because then u inverse identity u inverse
Yes, yes,
u1.
yes. Hmm.
Yes, sir.
Right. Here it is orthonormal. Everything is there actually. Orthogonality, everything is there. This one is a quadratic form. I'll not do today. That I'll do. I mean, all the quadratic form I'll do in the next last one. Let's do this one. What it says: let A and B be n cross n real matrix and C equals to A B B A. Okay, which of the following statement are true? If lambda is an eigenvalue of A plus B, then lambda is an eigenvalue of C. If lambda is an eigenvalue of A plus B, then lambda is an eigenvalue of C. And the second is the lambda is an eigenvalue of A minus B, then lambda is an eigenvalue of C. If lambda is an eigenvalue of A or B, then lambda is an eigenvalue of C, and all eigenvalues of C are real. So A is a real matrix. Okay. So C equals to A, B, B, A, right? So all eigenvalues of C are real. That is not true. Why that is not true? Because you can take let's take A is equals to 0 1 minus 1 0 and B is equals to 0. So then what you will get, C is equals to 0 1 minus 1 0 0 0 0 0 0 0 0 0 0 1 minus 1 0. So now if we take C minus lambda I, what you will get, that
Yes,
will
sir.
be,
Plus minus I. Plus
yes, plus
minus I.
minus I. So therefore, all eigenvalues are not real. So you can get that. So therefore, determinant of, you can get directly. I will just write. If I write determinant of this one or matrix, this one will be lambda square plus one whole square, right? So therefore, eigenvalues
Yes.
are plus minus identity repeated twice. So therefore, option D is, I think D is written. 4 is false. Option 4 is false. True. So therefore, this is not true. Therefore, all other thing we'll try to do it in single stroke if it is possible. Let's try to do A and B as a matrix. If let lambda belongs to R, be an eigenvalue of A, then whether then that implies there exists a vector like x1 x2 in R2 such that okay, not x1 x2, this is a n. So basically x1 all the way xn in R2 Rn there exists such that a there exists x is equals to this one. So therefore ax is equals to lambda x, right? This one is the thing. So now what I have to check is that whether lambda is an eigenvalue of C. So if lambda is an eigenvalue of C, then what I will have, A, B, 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 A, then mm, there must exist a vector x1, y1 all the way y2n that will be equals to, you can break it like two form, and one is y and one is y, one y2, that is in Rn, where each one, that one equals to a y1 plus b y2, and this will be b y1 plus a y2. So this will be equals to y1 y2. This should be equals to this one. So therefore, what I will get, a y1 plus b y2 is equals to y1. And if lambda is the same eigenvalue, okay, if lambda is the eigenvalue, what I have to get, lambda is the eigenvalue. If lambda is the eigenvalue of a, and if lambda is an eigenvalue of C, then we should have this way, right? We should have this equal to lambda. So therefore it will have lambda one is equals to lambda equals to this one, and by1 plus ay2 is equals to lambda y2. But this is also some not giving anything. If x is an eigenvector of lambda, then other eigenvector need not be similar to that one, right? I think we have to keep counterexamples possible. If lambda is an eigenvalue of a plus b, a plus b
Sir,
is,
if we take, sir, eigenvector V of A plus B, sir.
I think, yeah, if we take x and 0, that will work, I think. Is that what? That will work? Now, what you were saying?
Sir, if we take eigenvalue vector of A
A
plus
b,
minus B as, sir, V, and define U as V plus minus B column wise, sir.
defining u equals to
U is equal to column wise, sir, V plus minus V. Column wise, sir. Plus minus V. Column
plus,
wise.
column wise,
Plus minus V.
plus minus b,
Yes, sir.
minus b, like that way.
Plus minus. Plus or minus, sir.
Plus or minus, okay, that one.
Ah, yes, yes.
If you replace this one,
Then it
plus
will be,
just,
sir. Uh,
so
this
then
will be
ab
eigenvalue of
minus bv.
where V is the eigenvalue of, sir, A plus B.
Oh, that one will work. So let go that one. Let first go to that one. Then.
I
That
think
one
that
will work.
zero will also work. I think
Huh?
zero will also work, sir. I think if you
Zero.
take B zero, you are
B zero.
defining.
No, zero will not be that way. That will not. Okay, let me just. Yeah, that one is there is a problem. I see. I've seen. Okay. Oh, okay. Okay. I think, yeah, zero will maybe zero what? Okay. What it says, first one, let lambda is an eigenvalue of a plus b. So that means there exists a vector x in Rn such that a plus b whole lambda is equals to lambda x, right? And now what I have to show, a b b a, I have to find a vector such that that will be equals to lambda into that vector. Okay, so if I get this one with this one, so what I'll get, a, this is wrong.
AX plus
Uh,
BX.
this one will work, bx equals to lambda equals to, then this, if I take this one, then what will have, ax plus bx and bx plus ax, and that will be equals to lambda lambda x, right? So therefore lambda x, so therefore as x is not equals to 0, therefore x is not equals to 0, so therefore lambda is an eigenvalue of lambda is an eigenvalue of c, so therefore first option is correct. First option is correct, and I think other two option will be false, but let's check. So if lambda is an eigenvalue of a minus b, then whether lambda is an eigenvalue upon it, let's a
This
minus,
is also true.
yeah, this is also true. A minus bx is equals to lambda x. That implies there exists an x belongs to R n such that this will happen. So therefore a b b a, one have to take this one, we have to take x minus x, right? I think this will have a b ax ax minus bx bx minus ax. So this will be equals to a minus b whole x. This is equals to minus a minus b whole x, and that is equals to x, that is equals to lambda x, that is equals to minus lambda x, that is equals to lambda x minus lambda x. So this implies that x minus x not equals to 0 as x not equals to 0. So that implies that lambda is an eigenvalue of C. So therefore, this second option is also true. Third option, I think it will be false. Let's give an example, counter example, so that may work. So if I consider I, uh, if I consider all our identity, for example, like all are identity, B is also identity, so that will be, let's take something like 1 0 0 0 1 0 0 0 1, like that, 1 0 0 1 1 0 0 1. So what we'll get here clearly says that this is the matrix, for example. So what will be the eigen value of this matrix? 1 is an eigenvalue or not, first of all.
So this is you are considering C,
This is we are considering as C. This is the A, B. A,
but
B
A
both are
are
same.
equal. Yes, sir. Yes, sir. Yes.
So,
So this
so,
will not work, I think, because one are eigenvalues.
so 1, 1, 1. No, no, here 2 is an eigenvalue. 1, 1, 1. Whether 1 is an eigenvalue or not, that we have to check. Because
Sir,
1 is
eigenvalue
eigenvalue.
of A.
Eigenvalue of A is 1. Eigenvalue of B is also 1. And there is no other eigenvalue of A and B. So, whether for this matrix has eigenvalue, all are 1 or not. Obviously, all
Ye-
are not 1. One eigenvalue is 2, clearly it is visible. Because row sum, column sum,
Yes, sir.
all are
Yes, sir.
2.
Correct.
So, but
Yes.
but but what I have to say that whether one is also an eigenvalue or not, that we have to check. So
Yes, sir.
let's do that one, because that is what we have to do. There is no other option. At least for this one, if I am able to take another example, then this different thing. This is 1, 0, 1, 0, 1 minus lambda. So this is the matrix. So what is the determinant? Determinant is 1 minus lambda. Oh God. This is okay. I'll take some sort. I'll try to sort it. Let's take this one. So one is eigenvalue. Only one is the eigenvalue, and zero is also. So A A has one is an eigenvalue, and B, zero and one are the eigenvalue, right? So therefore
Yes.
it will be zero. I just want to make it easier. That's the main point, right? So this is the thing. There is no problem. I think 1 minus lambda into this determinant, and this determinant is 1 minus lambda cube. Mm, Minus here plus 1 into this one, this and this will you cancel out. So the determinant of 1 minus lambda 0 1 0 0 0 0 1 minus lambda. What is the determinant of this matrix? Determinant of this matrix is 1 minus lambda minus of 1 minus lambda. So this one is cancel out. So 1 minus lambda. So this is
Zero
equals to 1 minus lambda cube square, right?
minus lambda square.
This is correct, right? Minus 1 minus lambda, you have to cancel out this one. So 1 minus
Correct.
lambda, this is 1. So therefore, we can take 1 minus lambda square and 1 minus lambda whole square minus 1. So therefore, 1 minus 1 is an eigenvalue, that's clear. Whether, but 0 is not an eigenvalue. That's the main point. No, 0 is an eigenvalue. 0 is an eigenvalue. Minus 2 lambda plus lambda square minus 1.
Yes,
So
sir.
0
Zero
is an
is an
eigenvalue.
eigenvalue.
So 1 and 0 both are eigenvalue. So this is not going to work. So whether this is true, or if A is an eigenvalue of something, X is an eigenvalue of A.
Sir, if
So
we are able to
prove.
produce sir, a matrix,
Huh?
if we take sir A as nilpotent matrix,
Hmm.
and if we are able to find we are able to form matrix C as non-singular,
Non-nilpotent.
non-singular, sir.
Right, there is. Let's take B is equals to 0. B equals to 0. It is very easy example. A equals to I2. Then A, B, B, A, that is equals to I4. 0 is an eigenvalue of A, sorry, B, but not an eigenvalue of C. Done. Then, right? This is then false.
So there is or, but one is
If lambda
eigenvalue
is an
of A, sir.
eigenvalue of A or B, then lambda is an eigenvalue of C. Huh? So, or na. If lambda is an eigenvalue of A or B, then lambda should be the eigenvalue of C. So let 0 is an eigenvalue of A or B, right? 0 is an eigenvalue of B. That's why 0 is an eigenvalue of A or B. But 0 is not eigenvalue of C.
Yes.
It's true, no? I mean, there is no ambiguity, right?
But 0 is eigenvalue of B, sir.
Yes, 0 is an eigenvalue, but 0 is not eigenvalue of C.
Not eigenvalue of B.
Yeah, that is what asks, na? If lambda is an
But 1 is
eigenvalue,
eigenvalue of A, sir. And
yes,
1 is
we
eigenvalue of
have to
C.
contradict once, not twice, right?
So there is not A and B, sir.
Huh?
The A or B. There
A
is
or
A or
B,
B. Either A or either B.
either B. So 0 is an eigenvalue of B.
Huh.
Let's take lambda equals to 0. Whether this is satisfying up to this statement or not.
Yes, sir.
0 is an eigenvalue of A or B,
Yes, sir.
but 0 is not an eigenvalue of C, right?
Yes, sir. Yes, yes, correct.
Yeah. So I think this is thing. I don't know because this type of problem actually when answer key it displays this type of problem actually answer key gives some absurd situation. But this one is the another problem. So what it says, it is known that x equals to x naught in M to Z. That means 2 by 2 matrix with entries from integer. And is a solution of ax minus xa equals to a. Okay, and obviously for some a in this set, it is known that x is a solution. X equals to x naught is a solution of this. For some a belongs to this, which of the following values are not possible for the determinant of x naught? Okay, I think determinant of x naught. Which of the following is are not possible values of determinant of x naught. X naught possible values. Okay, so here it is saying that x is an operator x equals to x naught such that ax minus xa is equals to a. This is satisfying. Which of the following values are not possible for the determinant of x naught? X naught. Which of the following value can't be the values of determinant values of x naught? I
So
think
determinant x0 is equal to 0 means nullity is non-zero.
yes, nullity as determinant of x not equals to 0 implies that x is x naught is
Means nullity is non-zero, no, sir. So why we do not compute this kernel
sorry,
of the
x naught equals to if determinant of x naught equals to 0, then what will happen? No, I think better to is it, is it worth going through the okay okay. One thing it is clear that if this is the case, diagonal of a should be 0. Is it? Okay. Yeah, there is the thing. If this is happening, if this is happening, that should implies and x naught is not equals to 0 and x not equals to 0, then diagonal of a that should be 0. Is it true what I am saying? Let's take x naught equals to, I'm saying
so
that x
trace
naught,
to be zero, sir.
no, again diagonal will be. Not only trace,
Why?
diagonal will be. Why I am saying x11, x22, x21, right? And for example, A is an arbitrary matrix. I'm taking any arbitrary matrix, right? Okay. Then what is AX naught? That is equals to x11 A11 plus x12 A21, right? And what is the other diagonal entry? That diagonal entry will be x22 A12 plus x21 A22, right? You see the other two entries there. I'm not writing right now. And what is x naught A? X naught A is okay. Okay, I have written it. This is an x naught A. This is not A naught X. X naught x11 A11. This one with this one x11 A11 x12 A21 x22 A12 x21 A22, right? X naught A. This is that was x naught A. So what is the A naught X? Ax naught, that is equals to A11 x11 plus this one with this A11 x11 plus A12 x22. No, I was wrong. Why this interest? Okay. Sorry, I am making some mistake. So let's compute it completely. That would be better. So this is equals to x11 A12 plus x12 x11 A12 x12 A22. This one will be x22 A11 plus x21 A21, right? This is correct, right? This one is equals to what we have. This one is equals to we have A11, A12, A21, A22. This is the matrix. Sorry, sorry, not this one. Yeah, I don't know what happens. Just a minute. So maybe we should not go that way then. Which of the following values are not possible for the determinant of x naught? Trace of ax minus xa will be 0.
Trace A will be 0, sir. So the matrix A is, sir, 1, 1
Only
minus 1.
only that one that I understand. You sure the trace will be 0?
Trace is 0, na, sir, because if you take trace of both sides, then we
Okay,
know
what
that trace of
let's check.
A.
Let's check ax naught. Yeah, that's true. I think yeah, that's the only thing I think. Yeah, you are correct. A11 x11 plus A12 x22 and the other entry is okay, whatever there is
Sir,
that let
why
it
are
be.
you considering A as general matrix, sir? Why you do not take the A matrix uh,
No,
that
A is something this type of. I have to note that
yes, sir.
only
First
the
matrix is only possibility there,
only
sir.
possible. That is what we have to find. If we can find that one, then we are done. So first we have to ensure that that
Sir,
matrix is the only thing.
because sir, because it is given that ax minus xa is equal to A, and
Hmm.
if we take trace of both sides, sir, then we will get that trace is
So
0.
that is what I'm just trying to just. That is what
Yeah,
we are
okay.
calculating. Hmm.
Okay.
A21 x12 plus A22 x21. So let's look at whether we are getting yeah
The
this
trace of
term.
AB is equal to trace of BA. It is
Yeah,
always
that is yeah. Okay, that's true. Yeah, I am doing too much actually. Yeah, so we should
and
not
so
go that way.
trace of A plus B is equal to trace of A plus trace of B. So
Right,
from
right,
there
right, right,
we can
right,
conclude.
right, right, right. Exactly. Actually, that's true. That's true. Trace of AB equals to that way. Problem is that I have confused with the fact that maybe diagonal will be same, but
Yes,
trace will be zero. That's true. That you pointed out, but I have not that time.
yes,
I
sir.
have not
You have
observed.
pointed out earlier.
Yeah, but you also that time you reminded me, but I also forget. We know that trace of AB is equals to trace of BE, and trace is a linear function, right? trace of AB minus BA is equals to 0 for any A and B square matrix and B. Square matrix A and B. So that implies trace of A, that implies if AX minus XA is equals to A, trace of A should be 0. That implies A is the only choice. Only choice is the 1 minus 1, 1
minus
minus 1 minus 1.
1
Minus 1 1
yes
1 1 minus 1 minus 1, this one. So therefore if we have this one, so let's take x1, now take x1 general, x21, x22, this one with 1 1 minus 1 and other is that x11, x12, x22, x21, not 22, 21, x22, that one with 1 1 minus 1. So what we'll get, that will be, first one will be x11 plus x21, second one will be x12 plus x22, third one will be minus uh,
minus x11
x21
minus x
minus x11 minus x21, right? Third will be
yes sir.
minus x12 minus x22. This one, and that is also similar. X1, no, that will not be similar. X11, x12, and this will be x11
1
minus
1 minus
x12.
x12
Okay, yeah, that's true. X21 minus x22, that will be x21 minus x22, right? So therefore column
my
1,
yes sir.
so this is equals to x11, so that is equals to 1 1 minus 1, right?
Yes sir.
Therefore only option is that x11 plus what will get, that x11 plus x21 is equals to 1, right? No, sorry,
Sir, x11 will
sorry sorry
cancel out
sorry
now.
sorry sorry yeah, right. So this one will
x21
be
plus x12
x12 equals to half, right? Half, right? It will
no
be plus, oh x, this one we minus this one. Oh,
but
oh, sorry
sir
sorry sorry
x
sorry sorry,
x21
yeah,
is
I'm
there
just doing something upset
x21
completely.
plus x12 is equal to 1
That's true, that's true. And second one is that this one with this one, what will we cancel out?
and the thing will be
There is no
cancel out
cancel, no cancel out.
no
Okay, let's do the diagonal. I think yeah, x2 to cancel out.
yeah
So it will be x12 plus x, that is giving same thing, right?
minus x21
X12 minus x, no no no, yeah, minus x21
yes sir is equal to 1
minus 1.
this
So
will
that is
be
giving same thing.
why minus 1
Minus 1 is the diagonal, no?
yes sir
And there will be, okay, let's compute the cross diagonal. What is giving there? Let's see. X22 minus x11 plus x12, right? This one equals to 1, and I hope the other one will be giving similar thing. But what we know is that, so this is the thing actually, right? This is the thing. Okay, so what is the possible value of x12 and x21 are, some of them are non-zero, right?
yes sir
So we have the matrix like
and
x11,
also sir x21 x12 belongs to sir z
right, right. So therefore one of them should be zero. As as x is in m2z, x naught is in m2z, that imply either
sir this
x12
need
equals
not
to
be
0,
true sir
x21 equals to 0. No, no, no. I can do it, no?
no sir if you take 4 minus 3 then it is 1 if you take 6 minus 5 it is 1 it is not saying that these are positive integers
That is not said. That's true. That is not said. That is
sir
not said.
you can introduce sir here determinant of the matrix x
This one, right? Somehow.
uh,
x11, x22 minus x12, x21.
yes sir
So, um, smoothly. What it says that,
x11
No, but at least we can say that no x1 x21 none of them will be 0. They are integer only, we know this one, nothing else. x12 x22 x11 x12, ah, there it is, yeah, that is what I'm looking for. This plus this is 1, so therefore x22 minus x11 equals to 0, therefore x11 is equals to x22, right? Right.
Yes.
Hmm. So other thing what we can say is that x11 equals to x22, therefore trace mm, and also we have this one. Now I think it will work.
X11 is equal to X22.
Yeah, that is we have.
X21 plus X12 is equal to 1. Okay, sir. From there you got
Yeah, whether we have not missed anything from there. X1 minus x11 minus x21. Yeah, actually problem is that I'm trying to be over smart and I'm doing the
sir
mistake again.
X12 is there. Sir 2x1.
Yes, two.
Sir X12 is there, na? So you cannot put it as 1. This is 2 times X12. We have sir X21 plus X12 is equal to 1 from first equation.
Huh? So I have used na. Oh, that is two times.
Sir X12, sir suffix
How this is
are
two
not
times? It
same.
is. I
2
this is
times
going.
X1 2.
I understand. Understand. That I understand. What you are saying. That I understand. Mm, just a minute. If I just do it in very simply, maybe it will be easier. So okay, let me check whether I have made correct or not. This one with this term x12 plus x22, that's true. This one with this term, so x11 minus x12, that's correct. So therefore the term is x12 plus x22 minus x11 plus x12, right? Yes, that's true.
Yes, sir.
What is the second term? Second term is this one, that will complete 1 to 2 2. What is the second term? 1 1 1 2. So therefore this is equals to 1. Therefore 2x12 plus x22 minus x11 is equals to 1, right? This one with this minus x12 x22. This one okay. This one with this x21 x22. Yes, yes, I got it. Mm, minus x21 plus x22. So x1 x2, that is correct. So other diagonal is also not same. Okay, let's write the other diagonal. What it is says, other diagonal means this one. I just want to say this one. What it says, minus x11 minus x21 minus x21 minus plus x22, that is equals to minus 1, right? So therefore, what will get
Same, it
x?
will be same.
No, no, no. 1 to 2 1. This is 2 1, na? There is the extra thing.
Yes, sir. Yes.
X1 plus 2x21 plus x22 is equals to 1, right? I have removed the minus 1, so that will be minus 17.
Yes, sir. This is correct.
This one, right? This two is there.
Mm.
So now let's combine both of them. What I will get? What I will get? Oh, I x1 will cancel out. X21 will be there, and x22 also cancel out. Okay, these two we have. Okay, we have these three information. This one, this one.
Sir, I think
There's,
this equation is not correct.
I mean, you are saying that there must be some problem, right? This
Yes, sir.
multiplication. Okay, let's do it clearly. That would be better.
Sir, why you are taking x1, x11, x12? Simply take it as
A B
A
C
B
D.
C D, sir.
Yeah.
The subsets are making more
Right, right. Matrix is correct because we need trace should be
Yes,
0,
sir.
and that is
Yes.
only this matrix, right? There is no problem. So now let
Yes.
A B C D A X minus A B C D 1 1 minus 1, right? This one equals to E we have given minus 1. So what I will have A plus C B plus D
B plus D
minus A minus C
minus A minus C minus B
minus B
minus D
minus D. This one
minus
A
A
minus
minus
B
B, A
A
minus B,
minus
C
B
minus D, C
C
minus D.
minus D C minus D. This one equals to 1 1 minus 1. So therefore A plus C minus A plus B is equals to 1. First one. Second one is B plus D minus A plus B is equals to 1. Second one. Third one is minus A minus C plus D is equals to minus 1. Fourth one is minus B minus D minus C plus D is equals to minus 1, right?
Yes,
So,
sir.
so this one will give basically C plus B equals to 1, and this one will give
2B minus
2B
A plus D equal
minus
to
A
1.
plus D is equals to 1, and this
Yes,
one
sir.
will give minus A minus A plus
2C
2C
plus A
minus
minus D is equal to 1.
no, 2C plus A minus D equals to 1. This is equals to this will give, and this
This
will
is
give.
same. This is
Uh,
same at
this
first.
is same, right? B plus B. No, no,
Sir,
no, no, no. This is not same. B plus 2D. Oh, so DD cancel out. That is B plus C equals to. That is same. That is same. So these three are
sir,
there.
we want to sir calculate
We
determinant
want to
of.
calculate AB minus CD, what it
Uh,
is, right? This is what we want to calculate.
yes,
So
sir.
now, what is the not possible value? Obviously, we should not get the concrete value, right?
B. Yes, sir.
So even if we consider one of them, if we just assume
Sir,
C, let's write B is equals to 1 minus C, right? We know this one. So if we replace here, what I'll get? 2 1 minus C minus A plus D. Okay, that will not help much, right?
sir, put A as sir 1 plus D minus 2C.
A as 1 plus D minus that is same thing I'm just doing. The same thing it will work. Right now it will work. That's true. It will work. 2 minus 2C minus A plus D equals to 1. But what we know from here,
No,
2C is
no.
equals to 1 plus D minus A, right? Right?
Sir, I want to put this value in sir the determinant.
Here, here, here.
Yes, sir. So by the way, what is your matrix?
Matrix is A, B. Okay, okay, okay. B, C. What is this?
Mm.
Right?
Yes.
What I'm doing.
Now you
Okay.
can sir put A as sir 1 minus 2B
B.
minus
Now
1
that
plus
will be
D.
little bigger. So that's why I just want to do it little short.
Sir,
Let's
put
do this one once. Let's do this. Oh God, this is absurd.
sir
Yeah, I think there is
put
no
the
other way.
value of A sir in the determinant
Yeah, AD
by
minus BC. That is
uh,
equals to you are saying to put A equals to
A
1
is equal to sir 2B minus 1 plus D.
1 plus D minus 2C. Right?
No, no, sir.
This which one? This value.
Uh,
2B,
sir,
okay.
A is equal to 2B minus 1 plus D.
2B minus 1 plus D and
Yes, sir.
minus
Minus
D
B, 1 minus B.
1 minus
B.
B.
Yes. In place of C, you can put 1 minus B using
Yeah,
equation
that
1.
I understand. That I understand. But I
Now,
just
sir,
want to
now, sir,
2BD
calculate.
minus D plus D square minus B plus B square.
Now, this is a
Ha.
B plus D
Now
whole
it will
square.
give. It will give. That's 2. That's minus B plus D. Right? This will be B plus D whole square minus B plus D. I'm writing correct, right?
Ah, yes, sir.
This is the thing.
No. Sir, now sir take b plus d as x consider.
Okay,
So
okay.
it will be sir the quadratic equation, sir.
Then let
Let b
x is
plus d
equals
is
to b plus d. Then what will
yes, sir.
have x
And
square
ad
minus
minus
bx.
b, this is sir
The
determinant equation.
determinant, that's true. Minus determinant of the matrix X, right? That is
Hmm.
equals to 0. So therefore,
Now we have to sir find solutions of this such that the
so when we
solution
have real solution,
solution is sir integer we have to find.
yes, solution will be integer. So then solution X is equals to minus plus 1 plus minus root over of b square, that is 1, minus determinant of x, 4 determinant of x 4ax by 2, right? But then
Yes, sir.
and when x will be integer, whenever determinant, if I just replace, let's value replace the value, right? That
Yes,
will
sir.
do
Yes,
work.
sir.
If I replace value
Hmm.
x equals to 0, then that will be
Determinant
1.
x.
X is a determinant,
Determinant is if we assume that determinant x is zero, then
then
we
it
will
will
get
be
real solution.
real solution, that's true. So determinant
X
is,
is equal to plus minus 1 by 2. Now
so
track
even
back, sir.
except determinant of x equals to 0, I will
Uh,
not get any other value will not give us the real solution, right? Because all other are greater than 0, right? So if you replace here, we have 1 minus 4ac, right?
1 plus, there will be some plus, na? Because sir,
Oh, 4ac,
minus
right.
minus 4 AC, so
Right.
AC is a
So
minus
for
sign
determinant
determinant.
x is 0, then we'll get x is a positive solution. But if we replace x, determinant of x is equals to what are the value, all other value of 2, 6, 10. So if we replace 2, 6, 10, so if you replace t, 2, we'll get 9. 9 plus 1, 9 minus 1, we'll get integer. Okay. If we replace determinant x equals to 6, we'll get again. If we replace determinant equals to 10, 40 plus 1, 40, 11, that we will not get. But if we replace 6, then we'll get. So 0, 2,
25.
so
Uh,
we'll get now 5 and plus minus 1 is there. So 5, I mean either it will be
so
3
why
or it
you
will be
have?
2.
Yes, sir. Correct,
If we
correct.
replace 2, if we replace 2 there, then it will be 8 plus 1, that is 3. That means 3 plus minus 1, that will be 2 or 4. So that means we will get the integer solution, right?
Hmm.
So b
Hmm.
plus d will be integer. So I
Yes, sir.
think that is the possible choice I think one can give. Give that 2 and 6 10 is not the answer. 0 2 1 6. 0 will be 0, 0 will be also solution, right? Because if it is 0, then it will
So
be,
we have to check, sir,
no, 0 is
because
just,
we are getting some minus 1 by 2. No, no, sir. Plus 1 is also there. Okay, okay.
yeah,
Correct.
minus plus 1 plus
Yes, sir.
minus root under
Value
of
of x will
1
be, sir,
by
0,
2.
1.
So either 0 or 1 is the
Ah,
right. So 0 or
yes,
1
sir.
both are
Yes, sir.
integer.
Correct.
So 2
Yes.
6 10 are the, see, 10 is not the case. 0 2 6 is the answer. I think this is
I was
correct.
sir, thinking about, sir, if there is any sir, simpler solution. That
I
is why
think this
I
is
asked.
simpler solution. This is simpler solution, but the fact is that if we have done it properly, actually I have made very wrong steps, and
Yes, sir.
after that we have done whatever. Okay.
Sir, if we
So
can relate simply, sir, rank and sir, something.
yeah, I understand, but I don't know. Just in okay, actually, this is something. Maybe there is an easy trick. I am not able to,
Yes, sir.
but I am not able to right now able to recall.
So we can discuss it in next session if
I
if
I'll
you
try to
get.
look at.
Yes, sir.
Okay, let's do one more problem, and after that I will go back to the. This one is not done. This one is done. This one. Okay, this one is also done. Right. This one is the.
This is also solved.
This T1
Yeah.
T2 or the.
No, this is not solved.
So previous one, right? Which okay. Hmm. So this one will do, and after that I'll go to the what
Okay,
is
sir.
called the there's those problems, and after that I'll okay, let T1 T2 be linear operator on R square such that T1 T2 equals to 0. So therefore, if we consider T1, consider the what is called the standard order basis. So they are actually matrix, right? 2 by 2 matrix. Which of the following are necessary true? 0 is an eigenvalue of T1 or 0 is an eigenvalue of T2. Okay. So that is true. Why that is true? Because if T1 T2 is equals to 0, then the matrix representation will also be right.
Sir,
Yes.
product of sir, matrix representation of T2 and T1.
Right. That is what I am saying now.
Yes, sir.
Matrix representation of, I mean, A1, A2. If I write A1 is the matrix representation of T1, right? And I
Yes,
mean, with respect to the standard order basis, whatever we have, suppose we have basis of order 2, and A2 is equals to T2 with respect to that B, then you know that T1, T2, I mean, actually, then T1 x is equals to Ax, like that way. T2 x is equals to A2x, like that way, right? So, therefore, T1, T2 x, that is equals to what we'll have? That will be that A
A2X.
2x T1, this is something that is equals to A1 A2x, right? So therefore the matrix representation of T1 T2 with respect to the standard order basis,
A1, A2.
that is equals to A1 A2. But what we have, that is equals to 0. That is equals to 0. So therefore determinant of A1, therefore that implies that determinant of A1 into determinant of A2 is equals to 0, right?
Zero is
That
anyway.
implies that either determinant of at least one of them will be 0,
Yes, sir.
0 or determinant of A2 equals to 0, and this fact will show that 0 is an eigenvalue of either A1, either T1 or T2, right? So which of the following are necessarily true? So therefore first one is the necessarily true, right? 0 is an eigenvalue of T1 or 0 is an eigenvalue of
Yes,
T2, that's
yes.
true. There exists a non-zero vector W belongs to R square such that T1W equals to T2W is equals to
This
0.
did not be true.
Non-zero vector W such that this
Yes, sir.
should happen. This
Zero
need
is
not happen.
eigenvalue of sir, both T1 and this want to say that if we take sir T2 as
Zero is an
invert
eigenvalue but same eigenvector also. Zero can be
yes,
eigenvalue of both of them. There is no problem.
yes, sir.
For example, if I take 1 0 that way, there exists a non-zero vector W such that T1W equals to T2W. Okay. We know that this matrix with multiply with this matrix 0, right? 0. So you can take this one is the T1, this one is the T2, right? So
Yes.
here we have 0 is
Both
the
are same,
eigenvalue.
na? Sir,
Both are
both are
same.
same.
There is no problem. We can take. There is no problem. Here it is not said that they must be distinct. Just you want to give counter example for the second.
Yes, sir. So it will not be counter example.
Huh? It will not work. You are
Yes,
saying.
sir. Yes, sir.
Oh, there exist three. Right.
Basically, we want to, both are same, sir, and we want to show
Right.
that
Right. Right.
there does not exist.
Yes. Yes. I should not take the same. I mean, obviously same. Then there is the no. I will not be able to get. Okay. Let's take.
So T1 and T2 are non-zero or any linear operator, sir.
Yes, T1, T2, any non-zero, it is not said, linear operators. So
Sir,
one
if
can take,
we
you can
take
take with
T1 as
0.
zero,
0, yeah. You can
yes,
take
sir,
T1
and
0,
T2 as an identity,
right. It was
T2
identity.
as
Then
identity.
eigenvector, yes, yes. Then T1W not equals to 0. When there is a non-zero vector for none of them, then T1W, if T1 is the identity, then T1W equals to
Hmm.
W. That is not equals to 0. So therefore this is not correct, right?
Yes,
But T2,
yes.
T2 I have taken 0, so therefore this is 0. T2, T1 equals to 0. Obviously, this is not true because whatever I have few minutes ago given, this will work, right?
Yes, sir.
So then T1, T2 both are 0, but the product is, but none of them are 0, right? So the second is the third one is also not true, but let's give example. That will obviously not true. Because we have to give some interesting examples so that T1, T2 is equals to 0, T1, T2 equals to 0, but T2, T1 not equals to 0, right? We have to give example. I believe there is, but let's give an
Sir,
example.
what is the motivation of this thing, sir? You are saying that this is not true.
Because T1, T2 are not committing, because matrix are not committing, right? So what is the not committing? That means if AB equals to B, not equals to BA, so AB can be 0, but not BA not.
Yes, sir. Yes. Okay, sir.
That's why I'm saying. So we
AB
have to,
0, then BA not AB not need not be equal to BA. So there we can conclude.
yeah, so but we have to give that AB and BA such that AB equals to 0. So we have to give that AB. One, I mean, okay, so one can consider what are the AB, BA for which this is happens. So, but T1, T2 also needs to be 0. That is also one thing. So if I write 1 minus 1, and it is like 1 1, then first term is 0. If I want to make second term 0, I can give this way, right? And if I want to make all other term are 0, I can write this way, right? This is 0, right? This is T1, this is T2, right? Okay, now this is equals to 0 0 0 0, right? Now if I write T2 T1, T2 T1, what it is? 1 0 1 0
It will
1
not be zero.
minus 1 0. It will not be 0, right? Yeah, there is not 0. First non-zero term it is there. 1 0 minus 1 1. Even it is none of the entry are 0.
Yes.
This one with this minus 1, this one with this here. So this is not equals to 0. So that means last one is, third one is also false, right? Okay. So this clear,
Yes.
right? So okay, let's go to some of the problems, and after that I will come back. Though I have not. I think these are the problem you send me in mail, but you send also other problem which is not possible to take screenshot, and here I have to take right then and do it.
Okay, sir.
This is the problem. Just let me. Okay, just a minute. Okay. So this is the first question. Which of the following, which of the following are correct? That is the question. Just a minute. Which of the following are correct? Every self-adjoint linear operator T defined on an inner product space V is has an eigenvector. That is,
This is correct.
this is a statement. Hmm? Every self-adjoint linear operator T defined on an inner product space V has an eigenvector. This is correct, but why it is said this is not correct? This is correct, right? If I take a self-adjoint operator, linear operator, defined on an inner product space V, that must have an, if I just only take non-zero, but I think that is correct. One second. Oh no, no, sorry, finite dimension. This is not true. This is not true. We know that if V is a finite dimensional inner product space, and T from V to V be a self-adjoint linear operator, then T has an eigenvalue. But if V is not not a self-adjoint, V is not finite dimensional, then T need not be, T need not be, T need not have eigenvector, right? So we need not have eigenvectors. Therefore, an example is that, okay, an example is that if you take V is the space, all continuous, real valued or complex valued, that doesn't matter, or functions on cell space of all space of all continuous function, continuous complex valued functions on 0 to 1, for example, then for defining inner product from V cross V to the field F, that is equals to R, or the complex field, by F and G, that is equals to 0 to 1 Ft Gt dt. If it is complex valued, then we have to write Gt bar. If it is real valued, we have to write Ft. So Ft Gt, that doesn't matter. That will be same. So therefore, in that situation, we don't have any eigenvector. Why this is true? And why this is true? Because if and sorry, we have to take the t from V to V by T of F at T, that is equals to T into Ft. Then if T has eigenvalue lambda belongs to the field C, that is that is R or C. Even if I take C, because C is the bigger field, so there may be something one can expect. Eigenvalue. If F is an eigenvalue, if T has an eigenvalue, T has an eigenvalue. This is my handwriting. If T has an eigenvalue lambda with eigenvector V, F belongs to this vector space V, such that Tf is equals to lambda F, then what we'll have? We have that that lambda Ft is equals to Tft for all t belongs to 0 to 1. That implies that
T is equal to lambda.
t equals to lambda, and that implies that Ft is equals to 0 if t not equals to lambda, right? And if t equals to lambda, then Ft can be has to be 1 if t equals to lambda, right? Right. So but this function is not continuous, but this function f is not continuous, because unless ft equals to 0, that implies ft can't be eigenvector. Okay, because ft is 0, so if it is 0, then it can be eigenvector for anything. Okay, but why ft is 0? Because f is continuous, so if it is non-zero at some point, it should have a neighborhood on that point where it is non-zero. But here, if I even assume that ft is such that ft is equals to, this is I am not writing 1, this is I am writing star, possibly non-zero, right? Possibly non-zero 1. It can be 0 also, then still it is satisfied. But if it is non-zero and 1, If it is non-zero, then it has to be 1. That's different point. But if it is non-zero, there must exist a neighborhood around lambda where the function has to be non-zero. But there is no other point except this point. So that means there is no other neighborhood. Neighborhood means it should contain infinite number of points. Therefore, the first one is wrong. Second option is that for a finite dimensional linear product space V, the normal operator T will have an orthonormal V as an eigenvector. Okay, for a finite dimensional, this is the important thing. For a finite dimensional linear product space V, the normal operator T will have an orthonormal basis V as eigenvector of T. That's true. That is because the diagonalizable. That is true. Secondly, it says that for a finite dimensional inner product space V and the linear operator T, W be a subspace of V which is invariant under T, then the orthogonal complement is again invariant under T star. That is also true. And that says W is reducing under T. That is, I mean, if W is invariant under T and under T star, W is invariant under T, W star is under invariant under T star. Orthogonal complement. Right. W and W per both are okay. No. This is something different. Okay, but this is true. If for any finite dimensional linear product space, linear operator T and W subspace of B, which is invariant under T, then orthogonal complement of W is invariant under T. So that is already discussed in class. So I will not go. Every Hermitian matrix is orthogonally equivalent to a diagonal matrix. Hermitian matrix will be unitarily equivalent to the diagonal matrix, but that
This is
unitary
correct.
need not be orthogonal, right?
Uh,
Need not be orthogonal. Orthogonal means it is something like A transpose A is equals to identity, but we know what is that A star A is equals to identity. Obviously, A star is not A transpose always. So this is not for fourth option. I will write for option Option B, we know a Hermitian matrix is unitarily diagonalizable. Hermitian means self-adjoint, but that unitary matrix, that is, I can write, that is Hermitian matrix, right, H is, that is, there exists a unitary matrix U such that U inverse H U is equals to D, that is a diagonal matrix, right? This U need not be orthogonal unless we are in real vector space. We are in real field situation. If we are in real field situation, then it will be, because in that situation, Hermitian matrix is orthogonally unitarily equivalent to the diagonal matrix, and in real field, I mean, if we are considering the vector space over the real field, then that that unitary matrix has to be the orthogonal, because in real field, unitary means orthogonal.
yes.
Yes, yes. So therefore, the last option is incorrect. Let's go to another problem. Okay, this is something short problem. Let's problem seems short. But it says consider a matrix A equals to ABCD. Matrix A is normal matrix if and only B equals to C, B equals to C to the power I theta, B equals to C to the power I theta, B equals to minus C. So if and only. So obviously you can look at
Option B.
the option B is there. So oh, theta is complex number. Theta is real number. There theta is not complex number. That will be, this one is correct. This one is correct, but I mean, how just one can I say? Okay, A is normal operator, so let's write like this way. C, A, B, C, D, all are complex number, right? This one is there, and so this will be A star. So A star is A bar, B bar, C bar, A bar, right? This one is equals to A, B, C, D with A star, A bar, C bar, B bar, A bar. So what we will get? We will get mod of A square plus mod of C square, right? Is equals to mod of A square plus mod of B square, right? So what we'll get? Mod of B square is equals to mod of C square. And so therefore it is saying that B is equals to C into e to the power I theta for some theta is in real number. Why? Because this is very easy. Because if B is a complex number, B is a complex number, then we know that B can be written in terms of B into e to the power I theta for some theta is in R. This is called polar decomposition, right? Mod B into this is the argument, this is argument, this is the magnitude, I think. This is the magnitude it is usually called. Okay, so whatever. This is the thing. So therefore, if I B is something like that, C will be equals to mod C into e to the power I theta dash for some theta dash into real. So therefore, if I consider mod B square is equals to mod, so therefore, if mod B equals to mod C, then one can write it as mod B into e to the power I theta dash, and that can be written into mod B into e to the power I theta into e to the power I theta dash minus theta, right? And this is equals to B, so this is equals to B. So I am doing in the reverse way. That is something same thing. C into B. So that is something e to the power I theta dash minus theta. That is something real because we theta and theta dash are real. So this is done. So all other into will be necessary. This as it is said that if and only. So therefore it is saying that A is normal. That means B have to be equals to C or B has to be. This is then not correct because we can take theta something for which this is not 90 degree or not. Yes, you can take theta is not 90 degree or not 0, not 180 like that. Then we will get non-trivial type of answer. But C need not be this complex number. Okay, so this is also correct. So I think next there is the Hermitian form. Yeah. Okay, so I'll use little bit of definition of Sesqui linear form. Then I have to do this one. So Sesqui linear form. Sesqui linear form. What it says? Let V be an inner product space. Okay, over C complex field. Then a map F from V cross V to C is said to be Sesqui linear form if f of C alpha plus beta comma gamma is equals to C into f alpha comma gamma plus f of beta comma gamma for all C belongs to the field complex and alpha beta belongs to the alpha beta gamma belongs to the real vector space, inner product space, belongs to the inner product space. And second is that alpha comma C alpha plus C beta plus gamma, that is equals to C bar f of alpha comma beta plus f of alpha comma gamma. This is same for all C belongs to this one. So that means linear in first variable, antilinear or conjugate linear in second variable. But the interesting fact here, what is that we can take this one as the real. There is no problem about that. Then, then this conjugate linear will not be there. Then it will be linear in both variable. When we take V is a vector space over real field, then that is called, then F is called bilinear form. When we take V as an inner product space over R, then the form defined by this way, then the bilinear, then the function define, then function if defined this way is called bilinear form. Okay, so that means everything is in real settings, then it is called bilinear form. So the problem, what it says, V be the C2 inner product space equipped with the standard inner product. Standard inner product that alpha is something and beta is something. In V, which of the following is or are Sesqui linear form? So there is only one option. So this is obviously okay. So if I consider a first one is not true. Let's say alpha beta is equals to 1. Okay, so let's A. Then f of alpha plus beta into C gamma,
Sir,
what it will
C
be?
and D. Option C and D.
These are okay. So okay, let's visually check. So, but what it should be? But it should be f of alpha comma C bar, f of alpha comma gamma plus f of beta comma gamma. So even if we take C is one, it has to be this. So it has to be two, right? So therefore, this is not true. Now the second one, f of alpha beta is equals to x1 minus y1 bar square plus x2 y2. You know there is the square, so that will violate. So let's even check. So then if alpha plus beta comma gamma x1, that where alpha is equals to x1 x2, right? x1 x2 y1 y2, beta is equals to y1 y2, or even one can take C also. There is no problem. We can take this one. So this one is given. So let's write f of alpha, comma c beta. C is a complex number. Then what it will be? It will be x1 minus cy1 bar c bar, that whole square, plus x2 into y2 cy2, right? cy2, because that is the c thing, right? So therefore, but this is not equals to, not is equals to, it should be c equals to f alpha beta. This is not equals to, which is actually same with c bar with f alpha beta x1 minus y1 bar whole square plus x2 y2, but that is not true. Here it is not true. You can clearly, you can check x1 x2 satisfied, therefore this is, so this is also not true. So therefore the second option is also not correct. What about the third option? F alpha beta is equals to x1 plus x2 square minus x1 minus x2 square. Option C is correct, you are saying?
Yes, sir.
I think option C is not correct.
Sir, expand it, sir. By the formula A square minus B square.
Yeah, right. That is actually 4AB, right? So therefore, here it is same option C. That's true. That's true. A alpha beta is equals to x1 minus y1 square minus x1 plus y1 square, right? Oh no, sorry, x1 plus this one and x1 plus y1 bar square minus x1 minus y1 bar square. So there it will be 2x1 y1 bar 4, right? You know this is linear. You can do anything. This is true. This is linear. Linear in first variable and linear in second variable. So I am not doing anything here. This is true because you know this, wherever if you multiply C, C will get outside. If you multiply here, C bar will get outside. If you add, then you can get different, because this one is linear something, right? Linear in first variable and linear in second variable. Okay. The D option says that f of alpha beta is equals to x1 y2 bar x2 y1 bar. f of alpha beta is equals to x1 y2 bar minus x2 y1 bar, right? So here is even if you write f of alpha write it like this way. C beta 1 plus C beta plus gamma. Okay. But it will be where alpha is equals to x1, x2, beta is equals to y1, y2. Let's write gamma is equals to z1, z2. But in general, z is writing as complex number, but here I am writing like this way. Oh, this is complex number. There is no problem, right? So therefore, here it will be alpha x1, x2, f of this one, comma c1 y1 plus z1 c2 y2 plus z2. So this one equals to, it will be x1 y2 bar, that is c2 y2 plus z2 bar, minus x2 y1 bar c1 y1 plus z1 bar, that is equals to x1 c2 bar y2 bar plus x1 z2 bar minus c1 bar x2 y1 bar minus x2 z1 bar. So here you can take c1 or c2, one same constant. I am writing c1 c2, this is same constant, c. C. So therefore, what it will have, C bar, C bar, x1 y2 bar minus x2 y1 bar plus x1 z2 bar minus x2 z1 bar. So therefore, this is C into f of alpha comma beta plus this is f of alpha comma gamma. So this is expected C bar. This is expected. So and the other thing is also, you can easily, similarly one can check. Similarly, one can check f of c alpha plus beta gamma is equals to c f of alpha beta, alpha gamma plus f of alpha beta gamma. Okay, so therefore this is the correct option. So these two are the correct options. Let's do another problem. What it says, given a Sesqui linear form on an inner product space R2 equipped with the standard inner product. So here we are in settings of R. So therefore there is no Sesqui linear. This is actually bilinear. Okay. So then matrix representation of, okay. So then I have to give the matrix representation definition a little bit. Okay. This is okay. This is enough. Matrix representation of a Sesqui linear form. Matrix representation Sesqui linear form. Let F from V cross V to the field F be a sesquilinear form on an inner product space V. Let beta is equals to alpha 1 all the way alpha n on linear form on n finite dimensional linear product space V, on a finite dimensional linear product space on a finite dimensional inner product space V with dimension of V is equals to n. Let let beta is equals to alpha 1 all the way alpha n be an ordered basis of V, then the matrix A is equals to AJK, where AJK is equals to F alpha K alpha J is called matrix representation of the Sesqui linear form. Sesqui linear form F with respect to the given order basis. Now the fact one thing is that if um, if we have not said anything, then we should have considered the matrix representation with respect to the standard order basis. Okay. So here we have, it is saying that sesquilinear form equal to the standard order basis. Already it is mentioned. There is not a problem. So what it's the question is that f of x equals to given by this way, f of x1 y1 comma x2 y2 given by 2x1 x2 minus y1 y2 plus x1 y2 minus x2 y1. Okay, x1 y1 x2 y2 that way. My handwriting. X1 y1 x2 y2, right? 2x1 x2 2x1 x2 y1 y2 x1 y2 minus x2 y1. Okay, this is the thing. So now, so what are the
So
standard order
option B is
basis?
correct.
Option B is correct. Okay, I don't know. Let's. This is standard order basis. Okay, 1001. This is the standard order basis. I think we have taken this one is the standard order basis. Be the standard order basis. Basis. So first one will be a 1010. What it will be? It will be 1010 x1 x2 both are 1. All other integers 0. So 2.
2.
This is 2. That's 2. And f of 10 comma 01. This will be alpha 1 alpha 2. That means this is equals to
One,
a11
sir,
and this is
Y2
a21.
will survive.
Yes, 10. So
1.
x1 is 1, x1 is 1, x2 is 0. So this will go, okay,
1.
and y1 this will go, and x1 y2 this one will survive, right? Right, 1. This is 2, right? This one. So a12, what is that? That is f of 01 comma 10, right? That will be, this is corresponding to x, y1 is non-zero and y2 is
Sir,
0, right?
Y1 X2 will
So
survive,
this will
minus
minus
1.
1, right? Minus 1. And obviously 2 is equals to f1, sorry, 0101. 0101. So this will be due to y1 y2, that is minus 1, right?
1.
All other into 0, minus 1. So the
Minus
matrix will be 2 minus 1 1 minus 1. So this is second one, right? This is second one, right? I have written correctly. Yeah, this is second one. Okay, I'll check if there is any interesting problem. Okay, I think ninth problem again. Ninth is something one we can do, and after that I will try to take one of your problem which you first sent. What is this? This one I will do. I don't know what it is. This. Let's do this one. What it says? Then V with the space of all polynomials over the field with inner product. This one. I think we have discussed this one. Tg equals to fg. Okay, fg. T star denotes the adjoint of then which of the following statement is are correct? T star does not exist, that is or not, that one thing. And T star does not exist. Okay, so you know that this is called multiplication operator, and that is very interesting operator. Multiplication by phi f. Sorry, f is a fixed, right? Consider a function f in v, and a linear operator t on v defined by this way: tg is equals to fg. This is called multiplication operator. Multiplication by coordinate. Multiplication by f, okay, belongs to the vector space v. Okay, so what is a t star? So I just want to find what is t of h. Let h is belongs to the vector space v, and th with some another element, a g h I j k l m n p p. P is another element. Let's write p in v, this one. So what I can write is that by definition of the adjoint, we can write this way. By definition of adjoint. Okay, first of all, why there will exist adjoint? If I ask this question, T star denotes the adjoint of the, then which of the following is or are correct? Okay, then first we have to consider why the adjoint will exist. So same thing it will work also. Same thing it will work. And what will be the adjoint? By definition this is okay. By definition this is right. There is no problem. H into FP, right? And by we know this is inner product 0 to 1 HT FT PT bar dt. So this can be written as 0 to 1 ft bar ht into pt bar dt. This can be written as inner product f bar h comma p, right? So this can be written as t of f bar, or some another operator. So therefore what we get, this is true for this is what, right? This is what we get for all p belongs to the vector space v. So therefore, what we get, as this is true for all t belongs to vector space V, so there we what we get, that t star h is equals to f bar h for all h belongs to the vector space V. So this is the adjoint. So what is the question? T star exists. That's first of all, first option is incorrect. The t will exist or not. Second option, that t exists as and is unitary. That is not true. Why I'm not true? That I just want to say. T exists and is a self-adjoint operator. That is also not true. And t exists and it commutes with t. These two will be not true, and this is true. But I will first prove the that will commute, that one. Note that for any h belongs to the vector space V, t star th, which is equals to t star fh, right? That is the definition of the th. That is equals to, by definition, f bar into fh, that is equals to f into f bar h, right? Because that is commuting. That can be written as t of t with f bar h. That can be written as t into t star h. That implies t star t is equals to t star. Now, if t is self-adjoint, then t star h is equals to th for all h belongs to V. In particular, if h is a map from 0 to 1 to the whatever the field C or R, maybe I don't know, maybe R, such that h of t is equals to 1, that is constant function, then that should imply t star 1 is equals to t1. But what it is, that is t star 1, t star h equals to what? T star h means f bar h, that means f bar into 1, that is 1, that is f bar, and this is f. But that not necessarily true. But this is not necessarily true for any f belongs to f. Not necessarily true for any given f in V. So from here, what you can get, multiplication operator, multiplication by a function f, that will be self-adjoint. I mean, first fact is that adjoint. I mean, if t of h equals to f h, then t star of h equals to f bar h. That is called adjoint. Second is that it will be self-adjoint if f bar equals to f. That means f is real valued. Oh, sorry, this is real valued, right? No, complex value. Complex value. So therefore, f bar need not be. This is real then. Sorry. F bar need not be, because f is a complex valued function, right? Here it is, f is taken as an arbitrary. Consider a function f in V and linear operator. So f bar need not be f. You know what is mean by this f bar equals to f, means f of x is equals to f of t equals to f of t bar for all t belongs to the interval 0, but that is not the case. So therefore, no, it is not self-adjoint. Second is that not unitary. Note that t star will be unitary if and only if t star t equals to t star is equals to identity. That means for any h belongs to V, or if h equals to 1, that is the constant one, this ht, then what will get, t star t1 is equals to t star 1, that will be equals to 1, that will be 1 because identity. But what it is this, that first one is the f dot 1, that is f itself. Second one is the f bar, that f bar which is equals to f into f bar equals to 1. That implies mod of f square, that will be 1. That is what I just want to mean, f of t square, mod square equals to 1 for all t belongs to 0 to 1. But that is also not necessarily true always. But this is also not necessarily true always, right? Handwriting. True always for a given f belongs to V. Okay, now I will quickly try to solve a problem which you send another the picture. Okay, this is quadratic rule. Matrix P. Consider a matrix to over the field assignment. Which of the following matrices are of the function? Which of the present matrix is P over Q? Right? Put it there. Okay. Okay, so one problem I will do. Problem, what it says, consider a matrix A is equals to Aij, this is 5 cross 5, and 1 less than equals to I, less than j, less than equals to 5, such that Aij is equals to 1 by Ni plus Nj plus 1, where Ni, Nj coming from the natural number n. Then which of the following case A is positive definite matrix? Then which of the following case A is positive definite, but positive definite matrix is also not discussed. Positive definite matrix is also not discussed. So I will do this one because that needs a little day. You can write x equals to greater than 0. That's all. Positive definite is not discussed. I think not discussed. So okay. So then next one. Consider the matrix A equals to 0 1 1 0 over the field rational number of rationals which of the following matrices are of the form P transpose AP for a suitable 2 by 2 invertible matrix P over Q. Here PT denotes the transpose. Here PT denotes the transpose of P. So option 1, 2, 0, 0, minus 2. Option 2, that is 2, 0, 0, 2. Option 3, that is 1, 0, 0, minus 1. Option 4, that is 3, 4, 4, 5. It is which of the question? Which of the following matrix are of the from this one? Okay, so A is the matrix given 0, 1, 1, 0, right? So is rational which of the following matrix are of the form P transpose AP for a suitable 2 by 2 invertible matrix P over Q. So here you can note that A minus lambda I, that is equals to minus lambda 1, 1 minus lambda, right? So that is equals to lambda square minus 1. So that implies that lambda equals to plus minus 1 are eigenvalues of A. Eigenvalues of A. Now A minus I for lambda equals to 1 whole into, if I write x1, x2, what I will get? You know that there exist. You know that there exist. Okay, for first three option, we just want to get the matrix. We know that there exist two eigenvalues, so two eigenvector will be there. So this will be diagonalizable. That's true. But let's find those vector which is making that diagonalization. So x1, x2 equals to, I'm writing x1, x2 equals to, this will be A minus identity means minus 1, 1, 1, minus 1 whole into x1, x2, that is equals to minus x1 plus x2. This is equals to x1 minus x2. This is equals to 0. I mean 0 means 0, 0. That implies that x1 equals to x2. That implies 1, 1 is an eigenvalue. Sorry, that implies 1, 1 is an eigenvector. 1, 1 is an eigenvector of A corresponding to lambda equals to 1. Other one is that A plus identity whole into x1, x2, that is again 1, 1, 1, 1 and x1, x2. If that is equals to 0, 0, what we will get? We will get that 1 minus 1 is an eigenvector of A corresponding to 2 lambda equals to minus 1. So I mean you can directly here get what is the answer. Answer will be 1 and 3. These two are the correct answer. So 2 and 2 will not be. What will not be, that I will share. But 4 is also not be. Why 4 will not be? That is also the
Third is
same.
also not.
Third is also not true. No, I think we can do the
Yes.
scaling. Na? P needs to be invertible. That's why. Third will be true. You know that diagonalizable. Here the eigenvectors are 1 or minus 1. So this is the diagonal. Um, saying correctly. Okay, so let's check. Third is not your saying. So don't make any. So P, let's write P. What is the P? P is equals to 1, 1, 1 minus 1, right? So this is the
Yes, sir.
P. So what is the determinant of P? Determinant of P is minus 1, that is equals to
Minus
minus 2. Okay, so what is the P inverse? P inverse equals to 1 by minus 2, that is determinant, into adjoint. And adjoint is diagonal will be interchanged and sub-diagonal, cross diagonal will be minus. So
minus one.
minus 1, 1,
Minus.
minus 1, minus 1, right?
Hmm.
So, but but it has to be equals to P transpose. Here it says that P transpose AP for suitable 2 cross 2 matrix P. Hmm. How one will get? Oh, we have to make something P. We can change P, right? We can change P. We have to change P such that P transpose PT. So let's write P is equals to square root of this. 1 by square root of this. And what I will get? 1 by square root of this, right? Or or determinant of no. Hmm, hmm. P equals to this, then P inverse AP is the diagonal one, 1 0 0 minus 1, right? But P transpose AP for a suitable 2 by 2 invertible matrix, but transpose. P is an unitary matrix.
So actually, we have to show that the matrix A is congruent to the given matrix A in, sir,
Which
options.
matrix is congruent to given matrix, right?
Yes, sir. Yes, sir. In over Q, sir.
Over Q.
Sir, we know results in, sir, complex and real, sir. Two
Means,
matrices over Q over C are congruent if they have same rank, and over R if they have same invariants. But over Q we do not. I do not know
oh,
actually.
oh. Then what I am doing, that is not the way then.
But these results are not true in over Q, sir.
I understand. What you are saying, that result is not true on over Q. Oh, right. It is congruent. That I forgot. Actually, that is quadratic equation related, right?
Yes, sir.
Hmm. Actually, it's better to add on the positive one. Okay, let's try once, and then we'll. Obviously, the matrix P will be like this type of things, if it is possible. Okay, for example, if one just for I mean, we know what is this is A is easy one, and let's write P is equals to A B C D. Okay, this is all our rational, right? Right now, A B C D, that is the transpose, and here A B C D. What I will get? First, I will get C here, C here, next C here, next I'll get A here, next I'll get D here, and next I'll get B here, and this is A, B, C, D. So this is equals to will be AC, 2AC, right? 2AC, 2AC, and this will be BC plus AD. This will be AD plus BC, same thing. So this will be BD, 2BD, right? This is the matrix. So any matrix will be this form. So therefore this is obviously fourth one is cancelling out, right? Fourth one is not there, right? So now whether we can choose BD such way that okay. So yeah, I think this will work. This will work. So let me remove this one. Later remove later. Okay. So what are the options? I'll write is these options are here. I think you also have that options access. So obviously the option 4 is not correct, right? That's clear because we have to make AB plus BC. This has to be same, but that no, that is also same. Oh, sorry, sorry.
Sir, option 1, 3,
If
and
I
4 are correct. In
so
sir.
if I write it AB equals to BC equals to 0, if AB equals to B equals to 0, then AB equals to minus BC, right? So then what we'll get A by B is equals to C by D, right? Minus D. So then if I take it is lambda, then what I'll get A equals to B lambda, C is equals to minus D lambda. So in that situation, P transpose AP that will be A equals to B lambda. So 2B lambda into minus D lambda. This is 0, this is 0, this is equals to 2 BD, right? This will be equals to minus 2BD 0 lambda 2BD. So that's why C is not correct. Sorry, C is correct, na? C can be correct.
C can be correct. D is also correct.
So we can choose, yeah. 1, 2 is correct, but D is also correct. 1, 2, 3 both are correct, right? If I take B and D, both are 1, right? For example, you can take B equals to D equals to 1, then we will get minus and lambda equals to 1 minus 1, then that gives 2. 2 is correct. If I take B equals to half, D equals to 1 and lambda equals to 1, then we will get minus, B equals to 1, B equals to 1, lambda equals to, B equals to minus 1, B equals to 1, lambda equals to 1. What we will get? We will get 2, 0, 0, minus 2, right? Lambda equals to 1, yeah, this is true. So that gives 1 is correct. So now if I take B is equals to minus half, B is equals to 1, lambda equals to 1, then what will get? Then I'll get B equals to minus half, that will cancel out, plus 1, B equals to 1, that is 1, and 0, minus 1, right? So that gives C is correct, right? C is correct. Now what about the this ACBD fourth one? Fourth one is correct or not? That is 3445. 3445 is correct or not? So whether the matrix is 3445, whether this one is correct or not? Obviously, these four options, this is correct, this is correct, this is correct. We don't, at least right now, we don't know whether this is correct or not. 3445. So what we get then? 2 of AC equals to 3, 2 of BD is equals to 5, and that DC plus AD equals to BC plus AD is equals to 4, right? So if we do square here, what we'll get? This is B square C square plus A square B square plus 2ABCD, that is equals to 16. So we just want to write it as in terms of BC minus AD square, that is minus 2ABCD, that is equals to 16 minus 2ABCD, right? 2ABCD. No, plus 2ABCD. Okay, minus 4, minus 4. minus 4 ABCD, that will be 16, 2AB, 2B, 2AC, 2BD, that is will be minus 15, that is 1. So therefore what we will get, BC minus AD is equals to plus minus 1. So once we have BC plus AD is equals to 4, and whether this situation has solution or not, that is what I just am trying to solve. BC is equals to 5 by 2, okay, but that is not possible because both are, no, both that is possible. What is the problem with that? BC is equals to 5 by 2 and AD, so then what is the AD? AD is equals to 4 minus 5 by 2 or 5 by 2 minus 1, 8, 3 by 2, right? So BC AD this way. If I take BC plus AD is equals to 4 and BC minus AD is equals to minus 1, then BC will be 3 by 2 and AD will be, actually they are symmetric, I think. AD will be 5 by 2. So that means they are symmetric, something like that. So AC, BD, all this thing is there. So what we have, AC is equals to 3 by 2, BD is equals to 5 by 2, AD is equals to 3 by 2, BC is equals to 5 by 2. So what we can say is that C by D is equals to 1, but here we are getting also C by D equals to 1, so C equals to D, right? And here we have similarly, yeah, C equals to D. So I think we can have solution, that's what I just want to say. And if we take C equals to D equals to 1, then one can check A equals to 3 by 2 and B equals to 5 by 2. Then we are done. A, C, D, 1, A equals to 3 by 2, B equals to 5 by 2. Just replace this one. We have this matrix 2AC, BC, AD. We have this matrix 2AC, BC plus AD. Right? Mixed I'm writing BC plus AD, AD plus BC. BC plus AD and 2BD. 2BD. This one the. So write using this element, what I will get? I will get 2 C D, C is 1, A is 3 by 2, so this is 3. Now here B is 5 by 2, C is 1, 5 by 2, A is 3 by 2, D is 1, 5 by 3 by 2, that is 4. Similarly this is 4. Yeah, this is done, but this is not the way. So 4 option is correct, and whenever 4 option is correct, you would obviously need some work, because people will not believe that 4 option is correct. That's why 4 option is correct here, right?
Yes.
Okay, so I will stop here, and the next class will be the next and last class, that will be on Tuesday from 7 p.m. to 9 p.m. and there I will try to do mostly quadratic equations problems and all other I mean all other whatever the problem is there. So if there is